Hi everyone. Today we'll continue our discussion of time response of dynamic systems by focusing on higher order systems. Up until now we have talked about first order and second order systems. These are transfer functions with a single pole or two poles. Most realistic systems, however, have more than two poles, and they might have a couple zeros as well. So this is what we're going to focus on today, and we're going to learn how to model more complicated systems. When we have more than two poles, it's important to have a bird's eye view of how the system is doing, how many poles and zeros we have, where they are located. One of the ways that we try to visualize this is using pole zero diagram. This is nothing but the complex S domain. You have x-axis representing the real part of S and y-axis representing the imaginary part. And what we do is we indicate the locations of the zeros and poles, zeros with a circle and poles with an X. Suppose I have a system of the form g of s equals, let's say, s plus 1, s plus 2, I have an s plus 3, then a term s plus 4 squared, and another term which is s squared plus 2s plus 8. So let's say this is my transfer function. This transfer function has a numerator, which is s plus 1 times s plus 2, and a denominator consisting of terms s plus 3, s plus 4, and s squared plus 2s plus 8. The roots of the numerator are going to be the zeros of my transfer function, and the roots of the denominator are the poles. Let's start with the numerator. I have s plus 1 with a root at minus 1. So minus 1 is going to be a 0. So I will find minus 1 in this diagram, and I put a circle. The other 0 is going to be minus 2, representing the root to the term s plus 2. So at minus 2, I have another 0. How about the poles? I have one pole at minus 3. This is a root to the term s plus 3. So at minus 3, I add an x to indicate a pole. Then I have two poles at s plus 4. Remember that this is a repeated pole. In order to indicate the repeated poles, what we do is we use 1x per pole. So if, for example, this is minus 4, I put two x's here to indicate that this, in fact, is a repeated pole at that point. The next thing I have to figure out is the poles related to this term s squared plus 2s plus 8. These roots are going to be minus 2 plus minus square root of 4 minus 4 times 8, 32, divided by 2. If I simplify this, it's going to be minus 1 plus minus j, square root of 4 minus 32, that's 28, or 4 times 8, and the 4's cancel out, and you will have square root of 7. So you will have a, let's say, a minus 1 minus j square root of 7 and minus 1 plus j square root of 7. This now gives me a bird's eye view of how many poles I have, how many zeros I have, and where they are located. So for any type of higher order system, any system with more than one or two poles, we always start with the pole zero diagram. And remember, zeros, we indicate them with a circle, poles, we indicate them with an X. Now, whether a system has a single pole, two poles, or more, we would like to know the effect of these poles on the response of the system. In order to do that, let's look at it mathematically. Let's assume that I have a linear system. And as we have seen before, a transfer function can be defined for a linear system as the ratio of the Laplace transform of the output to the Laplace transform of the input, provided all the initial conditions are 0. So let's say I have a g of s, I have an input r of s, and it generates an output y of s. G of s is going to be a rational function consisting of, as I'm showing it on this slide, m zeros and n poles. So zeros that go from z1 to zm and poles that go from p1 to pn. At the same time, the input function can also be expressed as a rational function. You have seen these examples before. Unit step, or an exponential function, or a sine or a cosine, or a sine or cosine multiplied by an exponential function. All of these can be defined and expressed as a rational function in Laplace domain. So let's say my input, to be generic, consists of 1, 0 at A and 2 poles at B1 and B2. The output of this system is going to be the transfer function multiplied by input. If you multiply both these functions by one another, this is what you will get for the output. At the end of the day, I am interested in knowing the time response of the system, so I would have to find the inverse Laplace transform of y of s. And as you remember, the way to do this is to break this into partial fractions. So I do partial fraction expansion, break this into individual terms, individual rational functions, each function consisting of one of the terms in the denominator. So one is going to have s minus p1, as you can see here, s minus p2, s minus pn, b1, b2, and so on. You notice here that I'm assuming all the poles are real and simple. On the next slide, we will change this assumption, but for now, let's do it in the most simple way. If this is my y of s, I can easily find the inverse Laplace transform and find out what my y of t is. If I have a term a1 divided by s minus p1, the inverse Laplace transform, of course, is going to be a1 e to the power of p1t. Again, as you recall, shift in frequency domain represents exponential in time domain. So notice every individual partial fraction is going to be converted into an exponential term. So what does that tell me? If I have poles that are real and simple, the way I will see them in the output of the system is in the form of an exponential. Each pole is going to be reflected in the form of e to the power of that pole times t, p1t, p2t, pnt, b1t, b2t. So every pole is going to be reflected and seen in the form of an exponential function. So this is a very important observation for linear systems. Now, what if some of my poles are complex conjugates? If that is the case, for example, having a p1 and 2, which is, let's say, minus a plus minus j omega, I can follow the same approach for partial fraction expansion. And I can have an a1 divided by s plus a plus j omega. This represents the pole at minus a minus j omega, plus a2 divided by s plus a minus j omega, which obviously it represents the pole of minus a plus j omega. I can multiply these terms by one another, and I will get something like this. S squared plus 2a times s plus a squared plus omega squared. I have chosen some parameters for the numerator as plus b. We don't care about that right now. All we care about is the denominator. We have seen this before, how to break it down into a sine term or a cosine term. So let's not focus on that. Let's focus on the denominator. The denominator, I can look at the first three terms, these three guys, s squared plus 2as plus a squared. This, in fact, is s plus a squared. And then omega squared, I'm going to leave it just like that, omega squared. Regardless of what a and b are, you know that this term in Laplace domain represents a time function of the form e to the power of minus at sine of omega t ut and e to the power of minus at cosine of omega t ut. So if I have simple and real poles, I will see them in the response of the system in the form of a mere exponential. If I have complex conjugate poles, I will see them in the response of the system in the form of exponentials that are multiplied by a sine or a cosine function. So every pole is going to be viewed and observed in the output of the system. Depending on whether it's real or complex, the shape is going to be different. Okay, so I know that all the poles are going to be observed in the outputs. However, depending on where on the S-plane they are located, the shape of the output is going to be different. So let's say I have poles of the form minus A plus minus J omega. I'm just rewriting what I had on the previous slide. And I'm trying to be as generic as possible. So A can be anything, can be positive, negative, and omega can really be anything. If I have minus A plus minus J omega, I know that the response is going to be e to the power of minus AT, let's say sine or cosine of omega t. So that's what I know. Let's put these poles in different parts of this S-plane and see how the response is going to look like. Let's start with a simple case. Let's say I have a pole here. This is a pole which is negative and is real. So minus A is negative and omega is 0 because I don't have the imaginary part. Let's come back to this. If omega is 0, the sine of omega t term is going to be 0, cosine of omega t term is going to be 1. So I will have e to the power of minus AT, and again remember that minus A is now negative, times 1. So it's an exponential with a negative exponent, meaning that it's going to be decaying over time. So the response is going to look something like this. Let's move this pole a little bit farther away from the j omega axis. So here the shape is going to be the same because again my omega is 0, meaning that sine of omega will be 0 and cosine will be 1. However, now my e to the power of minus AT has a term which is more negative. So let's say this is e to the power of minus 10t compared to the previous case which was e to the power of minus 2t. If you have minus 10t, naturally it's going to decay to 0 much faster as time goes on. So despite the fact that the shape is still going to be exponential, it's going to be decaying much faster. So I'm going to be showing it in an exaggerated way like this. So this is a case when the pole is in fact a negative number. What if now it's a number which is complex with a negative real part? So let's say this is where I am. Let's say this is where I am for this pole. So here I have a minus A, which is negative, and my omega, as opposed to before, is not 0. So now I have an omega term representing a sine or a cosine. For simplicity, I'm just going to show the sine term. Cosine is going to be the same way. So here I'm going to have a sine function which is multiplied by a decaying exponential. So let's say it's going to look something like this. It's going to decay over time. If I follow the same logic as before and I move this pole a little bit to the left, farther away from the j omega axis, I will have the same shape, except that notice because the exponential decays faster, I will have an exponential multiplied by sine, so the sine is going to go down to 0 faster than before. Now let's move to the right hand side. Let's consider cases where I have poles on the j omega axis. Let's start with this case. I have a pole exactly at 0. In this case, my A is 0 and my omega is 0. If omega is 0, sine of omega is going to be 0, cosine is going to be 1, and then if A is 0, e to the power of 0 is 1. So I'm going to have 1 times 1, meaning that the response of the system is just going to be a constant line. Let's assume that I now have poles on the j omega axis, however not exactly at the origin. So here my A is 0, meaning that my exponential term doesn't exist. However, my omega is non-zero, so I'm going to have a sine term and a cosine term, which is not now multiplied by a decaying exponential. So it's just going to be an oscillatory function. So it's going to be oscillating like this. What if the pole is to the right of the j omega axis? So let's say I have a pole here. It's real, but it's positive. So in this particular case, minus a is a positive value. Omega is 0, so as before, sine of omega t is going to be 0 and cosine is going to be 1. E to the power of minus at, though, now has an exponent which is positive. So it's an exponential that does not decay, rather it increases over time. So the exponential, or the response of the system, is going to look something like this. I will follow the same logic, and if I move away from the j omega axis, I will now have an exponential that will grow at a much faster pace. So this is now going to be looking like this. And finally, if I have poles that have positive real part, and in addition to that complex part, I will have a sine or cosine function that, as opposed to previous case when they're decaying, here now they will be growing over time. So you will have something like this. And of course, if I move away from the j omega axis, this impact of growing is going to be exaggerated a little bit more. So it's going to be much bigger. What if I move away from the real axis? So up until now, I've been talking about moving to the right or to the left of the j omega axis. Let's say I move a little bit up. So let me use a different color and imagine my new poles now are somewhere here. If that is the case, I will get, compared to this pole that now I'm circling with color blue, compared to this pole, I will have the same level of damping because I have the same e to the power of minus at term, meaning that the decaying term is going to be the same. However, my omega now is going to be larger than the previous case. What is omega? Omega is going to be the frequency of that sine or cosine term. So in this particular situation, I am going to have, and I'll try to show it here, I will have higher frequencies compared to the previous case. I'm not sure if you can see this very well here, but what the point I'm trying to make is, in the red case, I will have a higher frequency, and as you can see, more number of oscillations during a certain period of time compared to the blue case. Now this is the general behavior of the poles depending on where they are located in the complex domain in the pole zero diagram. This j omega axis, any time that you have poles located on the j omega axis, you're going to have an oscillatory type behavior. When you go to the left side of the j omega axis, the response of the pole is going to be in the form of a sinusoid or just an exponential. In either case, it's going to be decaying over time. We refer to this part of the j omega axis as the left half plane. And then if you have poles on the right half plane, the behavior is going to be either in the form of just a simple exponential that is growing over time, or a sinusoid which is going to be growing over time. So this is the effect of poles on the response of the system depending on where the pole is located. Qualitatively speaking, when you add poles to a system, the system becomes slower, more sluggish. Consider this example here. Blue curve represents a system with two complex poles. As you can see, the system oscillates a little bit, so maybe you can see a little bit of overshoot around here, but it eventually settles to the final value, which is 1, rather quickly. If I add one more pole to this system, let's say a pole at -2, so a pole on the left half plane with a negative real part and no imaginary part. The response of the system is going to be shown by the red curve, and you see that pretty much the pattern is the same, a little bit of oscillation. However, the system becomes a bit slower. And if I add one more pole, let's say the green line where I have a pole at -2 and -3 in addition to the original poles that I had in the system, the response becomes even more sluggish. So it pushes a little bit to the right. So qualitatively speaking, again, adding more poles makes the system slower. How about zeros? Well, as you can probably imagine, zeros do the opposite. If you add zeros to a system, qualitatively speaking, the system becomes faster. You will see a little bit more overshoot and perhaps shorter rise time. Mathematically speaking, what zeros do is they change the magnitude of those individual terms that represent the poles. What do I mean by that? Remember that every time that you have a pole in the system, the pole is going to have an effect in the output in the form of either an exponential or an exponential multiplied by a sine function. However, each of these terms, either the e to the power of minus at or e to the power of minus at times sine or cosine, each of them are going to have a magnitude, a coefficient. The coefficients that essentially come from a partial fraction expansion. So let's say, for instance, I have a function which is 1 divided by s plus 1 times s plus 3. This, of course, using partial fraction expansion, I will break it into a divided by s plus a plus b divided by s plus 3. So now if I solve this system, I will find out what a is and what b is. What if I have a 0? If I have a 0, I'm basically just rewriting the terms that I have at the top. S plus 2 divided by s plus 1 times s plus 0. What would I do if I want to break this into partial fractions? As you remember, it's going to be the exact same procedure. So again, I will have a divided by s plus a, and I will have some b divided by s plus 3. If I solve for a and b in this equation, the values are going to be different from the previous a and b that I found. However, the scheme is the same. The procedure is the same. What does that tell you? If you have zeros in the system, the only difference that they will cause is essentially different magnitudes for a and b, different magnitudes or coefficients for those partial fractions. And you can see the solution here. When I don't have a 0, so my system is 1 over s plus 1 times s plus 3. Once I find a and b and also the inverse Laplace transform, I will get a function which has e to the power of minus t, e to the power of minus 3t with coefficients 1 over 2 and minus 1 over 2. If I have a 0 at minus 2, which I am showing here, I will do the same thing. Notice I will get the exact same exponentials. However, the coefficients change from 1/2 and minus 1/2 to 1/2 and 1/2. So the shape of the function in the sense of which exponentials are going to appear in the output do not change by adding a 0. However, the strength or the magnitude of each one would differ. And this is what zeros do in the system. Let's summarize what we have learned so far. Every pole is going to be reflected in the output of the system in the form of either an exponential or a sine or cosine multiplied by an exponential. When you have a bunch of poles, essentially the overall time response of the system is going to be the combination of all the individual responses. If you have access to a software like MATLAB, you can easily plot the response of the system and see, for instance, what the overshoot is or what your settling time, rise time, all these parameters that we're interested in. In the absence of something like MATLAB, though, you're not going to be able to look at a higher order system and identify all these parameters of interest. Because of that, a lot of times what we do is we try to see if our higher order system can actually be approximated by a lower order system. And when I say lower order, typically we mean a second order system, because for a second order system, I can quickly look at the denominator and identify what the overshoot is or settling time or rise time. Now, in order to have that successful approximation, you have to have 1 or 2 poles in the system that are dominant poles. A dominant pole is a pole whose response dominates the overall response of the system. In other words, a pole whose response will overshadow the time response of all the other poles in the system. Now, what do I mean by that? Let's consider an example where you have two poles, one at -1 and one at -20. The pole at -1 is going to give you a response in the form of e to the power of -t, and the pole at -20 is going to give you a response in the form of e to the power of -20 times t. Now, of course, each of these might have their own coefficients, and we're not going to be talking about that for now. So let's assume both of them have a coefficient of 1. So it's e to the power of -t plus e to the power of -20t. If I want to plot this, or plot both of these with respect to one another, let's say e to the power of -t will decay something like this. So exponentially and kind of slowly will decay to 0. E to the power of -20t, though, is going to be decaying much faster. So as time increases, the value of this function will go towards 0 at a much faster pace. So let's say e to the power of -20t will go to 0 like this. So you have one response corresponding to e to the power of -20t and another one corresponding to e to the power of -t. As you can see here, e to the power of -20t goes down to 0 very quickly, so you're not even seeing a lot of its impact on the output. On the other hand, the response of the system, if you add these two together, the response for the most part is going to be determined by the time response of e to the power of -t. That means that e to the power of -t, which is my first term here, is overshadowing the response, the overall response of the system. Now, if you have poles that are close to the j omega axis, the real part of this pole is going to be small. So that e to the power of, remember that e to the power of -at, when -a is small, that means that, or rather I should say, when a is small, this means that the decaying part is going to be very gradual and very slow. At the same time, if you have poles that are farther away from the j omega axis, that e to the power of -at is going to have a very large a, meaning that it's going to be decaying very, very fast, and you're likely not to see a lot of that dynamic in the output. These poles are said to be dominated by the slower pole. So the slow pole is going to be the dominant pole, overshadowing the response of the faster poles. Now, when you look at the pole zero diagram, you always look into the pole or poles, so you can have either one or two, the pole or poles that are closer to the j omega axis. Then you look at the next pole, the one which is farther away. If the difference between the distance of this closer one, which I'm showing it here with this arrow, and the one which is farther away is large enough, we can perhaps assume that the one which is close, which is a slower pole, that is the dominant pole. That is the one that will overshadow the other responses, will dominate the other responses. And this pole, which is farther away, is having a dynamics which will die out very quickly. We call these insignificant poles. Now, what is the rule of thumb? At least in this class, we consider a pole to be insignificant if its distance from the j omega axis is at least 10 times larger than the distance of the pole which is closest to the j omega axis, which is the dominant pole. So you always look at the poles that are close, look at the distance, and then you compare the distance of the one which is farther away from the j omega axis. More than 10 times, that should give you peace of mind that this pole, which is farther away, is insignificant, and I can ignore that. We can actually do the exact same thing with 0. So if you have a 0 whose distance from the j omega axis is more than 10 times larger than the distance of the dominant pole to the j omega axis, you can safely ignore that 0 as well. Now let's see this through an example. So here I have a transfer function of the form s plus 2 divided by s squared plus 2s plus 4, and I'm missing a 2 here, so this should be s squared plus 2s plus 4 times s plus 10. This system has 1, 0 at -2 and 3 poles. So this term is going to give me 2 poles at -2 plus minus square root of 4 minus 4 times 4, 16, divided by 2, which is going to be -1 plus minus j, square root of 4 minus 16. That's j square root of 12, which is 2 times square root of 3. The 2's cancel out, and I will have square root of 3. And then I have another pole here associated with this term at minus 10. Let's plot that pole zero diagram and indicate where the zeros and poles are located. So the 0 is going to be, if this is minus 1, this is minus 2. The 0 is going to be at minus 2. My pole, the complex conjugate poles are going to be at minus 1, minus j square root of 3, and minus 1 plus j square root of 3. And let me extend this a little bit to the left. So let's say that pole at minus 10 is somewhere over here. The distance between the poles that are closest to the j omega axis and the axis is essentially 1. The distance between the 0 and the j omega axis is 2, and the distance between this third pole and the j omega axis is 10. Based on the rule of thumb that we have, I can safely ignore this pole because its distance to the j omega axis is 10 times more than the distance of the closest poles. I cannot, however, discard the 0 that I have because it's pretty close to the j omega axis. So this can be a system with 2 dominant poles, which are these guys, and a 0. So I will approximate this with a g of a for approximate, which is equal to, I will only have 2 poles associated with the term s squared plus 2s plus 4. I will still have my 0, but now I got rid of that s plus 10, that pole at minus 10. However, when I take out that term, I have to make sure that the 2 functions, the original function and the approximate function, are completely identical over a large range of frequencies. So in order to make sure that is the case, I will place a gain of k here. I try to find k in such a way that both these functions are behaving the same way. One of the frequencies that we are in particular interested is the DC gain, which is the frequency of 0. So I want to make sure that the original function at 0 is exactly identical to the approximate function at 0. So let's plug in 0 and see what we get for g of s. I will have 0 plus 2 divided by 0 squared plus 2 times 0 plus 4 times 0 plus 10. This has to be identical to k times 0 plus 2 divided by 0 squared plus 2 times 0 plus 4. And from this equation, we can see that k is going to be 0.1. So that means that my original function, which is a third order system, can now be approximated by a second order system. However, notice that, let me erase this k. Here, instead of having that s plus 10, I now have a constant of 0.1. So now this is going to be the approximate lower order system that I will use to analyze the behavior of my original system. What is the benefit? If I show you this original transfer function and I ask you what is the overshoot, what is settling time, what is rise time, without having access to MATLAB, you're not going to be able to answer me. However, once I show you the approximate function and I say find these parameters for me, you can very quickly find out what each of those are. So this is what we do to approximate a high order system with a lower order equivalent. Okay, so if I have a higher order system, I may be able to approximate it with a lower order equivalent system, which has dominant poles, maybe first order or second order. And these dominant poles will determine the response of this new system, how fast it's going to be or how much overshoot it'll have. What if this behavior, this response is not good enough? What if the system is too slow? What if the system has too much overshoot? One of the jobs of a control engineer is to design a controller that forces a system to behave the exact way that I want it to behave. If I want a system to be fast, it has to be fast. If I don't want it to have overshoot, I have to be able to design a controller that makes the response smoother. So one of the things that we need to do is to see if we can actually find a way to move those dominant poles into some location that will give us desired behavior in terms of settling time, rise time, and overshoot. We're not going to be talking about those controllers today. This is a topic for later on. Later in the semester, we're going to be talking about different types of controllers and compensation techniques that will allow us to actually achieve that. But for now, let's go back to the notion of dominant poles. So let's see how I can relate the response of the system to where the dominant poles are located. You remember from our discussion on second order systems that a system can be overdamped, underdamped, or unstable. Underdamped system by far is the most common type of system, something that you will run into much more frequently in real world. If you have an underdamped system, you're going to have two poles, which are here and here. I apologize if you're hearing some noise in the background. My puppy is kind of trying to chew on something. Hopefully that's not too distracting. So let's say I have these poles, two poles, complex conjugate, with a real part of minus zeta omega n, which I refer to as the damping ratio, and the imaginary part, which is going to be omega n times square root of 1 minus zeta squared. Let me show these two poles on the S domain, on the S plane. So this is going to be the real part, which is minus zeta omega n, and this is going to be the imaginary part, which is now j omega n square root of 1 minus zeta squared. And you're going to have a negative value of it here at the bottom, which actually my picture is overlapping on that. If I look into this triangle, the triangle that I'm denoting as ABC, AC is going to be square root of AB squared plus BC squared. And if I plug in those values, I will see AB is going to be square root of omega n squared times square root of 1 minus zeta squared to the power of 2. So that will be omega n squared times 1 minus zeta squared. And then BC is zeta omega n. If I have zeta squared omega n squared, and if I simplify this, AC is going to be omega n. Now what is AC? AC is the distance of the pole to the origin. Notice that minus zeta omega n, or rather zeta omega n, is the distance of the pole to the j omega axis, so this distance here, but omega n is the distance of the pole to the origin. Why is this important? We're going to come back to it. But for now, just let's remember this. Omega n is the distance to the origin. Zeta omega n is the distance of the pole to the j omega axis. The last thing is this particular angle beta. Let me use a different color. So this angle beta. Beta, or rather cosine of beta, is going to be equal to BC divided by AC. Now BC is zeta omega n, and AC is omega n. So cosine of beta is going to be zeta, meaning that beta is going to be cosine inverse of zeta. In fact, I had it written here. So beta is going to be cosine inverse of zeta. So based on what zeta is, damping ratio, and what omega n is, the natural frequency, you can see how far away the pole is to the origin and at what angle. So beta is basically the angle between the line connecting the pole to the origin and the x-axis. Now let's remind ourselves of the response of a second order underdamped system. As you recall, the response is going to be sort of an oscillatory response. So if k is my final value, I will go towards that with a little bit of oscillation. This portion of it is going to be how much overshoot I will have, and then eventually I'm going to be settling in. For this, again, if you remember from our previous discussions, I have three parameters of interest. The first one is going to be the overshoot, which is how much over the final value I will go in percentage. Settling time, the time it takes for the response to settle within the plus minus 1% envelope, and rise time, the time it takes for the response to go from 10% of the final value to 90% of the final value. Now let's remind ourselves of the equations. So overshoot is related to zeta through an exponential function. Settling time is 4.6 divided by zeta omega n. And again, remember that zeta omega n is the distance of the pole to the j omega axis. And rise time, and this should be tr and not ts. So rise time tr is 2.2 divided by omega n, and again remember omega n is the distance of the pole to the origin. Now, let's say I have a system and I want its rise time to be shorter than some particular threshold. Let's call that threshold TR bar. So rise time is going to be 2.2 divided by omega n. And if I want this value to be less than TR bar, that means omega n for that pole has to be greater than 2.2 divided by TR bar. Going back to what we just talked about on the previous slide, omega n is the distance of the pole to the origin. So what does that tell you? If I want to have a smaller rise time, that means I have to have a longer distance between the pole and the origin. That means I have to move the pole away from the origin. If you consider a half circle with radius of omega n being this value, 2.2 divided by TR bar, whatever number that comes to, every pole that I have exactly on the periphery of this half circle, these poles are going to give me a rise time which is exactly equal to TR bar. If I want the rise time to be less than that, that means the distance has to be greater than that omega n. That means I have to be somewhere here, or somewhere here, or somewhere here. So as long as I have my dominant poles located in that shaded region, I'm going to get a rise time which is less than this particular value. I can follow the same logic and analyze a situation where I have a system with kind of a slow settling time, and I want to make sure that its settling time is going to be shorter than some particular threshold. So now I want its settling time to be less than some value that I call TS bar. Settling time is going to be 4.6 divided by zeta omega n. So if I want this to be less than TS bar, that means zeta omega n has to be greater than 4.6 divided by TS bar. Let's call this value some k. So that means that zeta omega n has to be greater than k. Now, what is zeta omega n? Again, from our previous discussion, zeta omega n is the distance of the pole to the j omega axis. So if I want to get a lower threshold, lower settling time than my particular threshold, I want to make sure that the distance of the pole is going to be greater than that k. So if this is k, any pole that is exactly on this line here will give me a settling time which is equal to TS bar. If I want a shorter settling time, a faster response, I have to put my poles somewhere in this shaded region. Any pole which is in this shaded region, and notice I always showed with the complex conjugate pair. Any pole which is in this shaded region is going to give me a settling time which is less than TS. And finally, we can extend that analysis for situations where we have a system and we want its overshoot to be less than a particular threshold. So imagine I have a system and I have a target overshoot of OS bar, and I want to make sure that I never exceed that percentage of overshoot. If I solve that equation for zeta, it will tell me that zeta has to be greater than this value, this number. Let's call this number k. So zeta has to be greater than k. Now again, go back to the geometry of the poles. This, use a different color. So this being the distance to the origin, and this angle being the angle between that line and the real axis, and the cosine of that angle, so the cosine of beta is going to be zeta. So if I want my damping ratio to be greater than that number k, that means I'm looking for angles whose cosine is going to be greater than that particular value of k. So here, let me replace this with k. So cosine inverse of k. The angles whose cosine is greater than k are going to be angles that go within this shaded region. So if I have poles exactly on these lines, I'm going to get a damping ratio, or I'm sorry, an overshoot, which is exactly equal to OS bar. But if I have any poles in this shaded region, that means the overshoot is going to be less than OS bar. So this is a third way that I can decide where to place my dominant poles in order to get that particular behavior in terms of overshoot. Let's see this in an example. So imagine I have a system with a pair of dominant poles, and it has certain transient behavior. It has a certain settling time, rise time, and overshoot. I want to know where I should place these dominant poles if I want the rise time to be less than 1.1 second and the settling time to be less than 4.6. So what I do is this. I say I want my rise time to be less than 1.1. I know that rise time is 2.2 divided by omega n. If this needs to be less than 1.2, that means omega n has to be greater than or equal to 2. At the same time, the settling time, I want it to be less than or equal to 4.6. This is 4.6 divided by zeta omega n. I want this to be greater than 4.6, which will tell me that zeta omega n is going to be greater than 1. Let me erase this. Greater than 1. So the ideal dominant poles for me have to have a distance from the origin, which is greater than 2, and a distance from the j omega axis, which is greater than 1. The best way to decide where the ideal location is to actually plot this in the S domain. So if I have my zero pole diagram, any pole that has a distance to the origin to the amount of exactly 2 is going to lie on a circle with a radius of 2. So this is going to be j2 minus j2, and this is going to be minus 2. So any pole that I have here, all of them are going to have a distance to the origin which is going to be equal to 2. So all the poles on that half circle, if I place my dominant poles there, they will give me a rise time of exactly 1.1 second. Since I want a rise time which is less than 1.1 second, that means I need a distance larger than 2. That means I have to look into the outer side of that half circle. So it's going to be pretty much anywhere outside of this half circle. So that's one. Second, let's look at the line that has a distance from the j omega axis equal to 1. Let me use a different color. So let's say this is minus 1. So this is going to be my line, and it has a distance of 1 to the origin. Now if I have any poles exactly on this line, what does that mean? Its zeta omega n is equal to 1, meaning that its settling time is going to be equal to 4.6. Since I want a settling time of less than 4.6, that means the pole has to be farther away from the j omega axis, so it means it has to be on the left side of this line. Now, if I want these conditions to be met simultaneously, that means the ideal location for my dominant poles is somewhere that is both outside of that half circle and to the left side of that vertical line, which, let me use a different color, which means is going to be somewhere here. So I will have, let me try to use a thicker line. So anything to the left side of this green thick line that I have is going to meet both criteria. It's going to be having a distance of larger than 2 and also from the origin, and a distance of larger than 1 from the j omega axis. Hence, both rise time and settling time requirements are going to be met. So let's summarize what we just learned. We talked about higher order systems where you have multiple poles, more than 2, and we saw that sometimes, not always, but sometimes it is possible to find an equivalent model, an equivalent system which is lower order but behaves the same way as the higher order system, as the original higher order system. And we saw that this system, depending on where the dominant poles are located, is going to have certain transient behavior. If I want to get the transient behavior that is desired for me, I would have to design a controller that relocates these dominant poles to the region which is more appropriate. And the best way to do this really is using this geometrical kind of analysis. And later on we will see that we can actually do this using MATLAB. And you will see where you should put the poles, the dominant poles, in order to get the behavior that you want. So we're going to stop here for now. Hopefully this gave you a good flavor of how we do the time response analysis of higher order systems. If you have any questions, you can either email me or you can leave a comment in the comment section, and I'll try to answer them as soon as I get a chance. Otherwise, I will see you for the next lecture when we talk about system stability.